going to discuss the classification of general second-order semi-linear PDEs with two variables. This is only good for two independent variables. If we have more than two, then we cannot do the job as we wish always. Okay, sometimes we can do so, sometimes we cannot. Okay. But for PDE with only two variables, so in our case we have two independent variables. One is x, the other is t. Yeah. Okay. So this is a general second order semi-linear PDE. So you can see that for the second order quantitative derivatives, we have they are linear, okay, with coefficients, and the coefficients A, B, C are function of x and t only. Okay, right. And the other terms can be very highly nonlinear, but we don't care about that at this moment. Okay, and we assume the coefficients function A, B, C are continuous differentiable. Continuous differential means that all their first order partial derivatives are all continuous. So they have partial derivative with respect to x, and also you have first order partial derivative with respect to t, etc. For B and C, they are all continuous. Open subset U, okay, of the x-t plane, right? And at least one of them are not identical to zero. If A, B, C are identical to 0 in this open set, then this is vanished, right? It is not a second order problem anyway. So I think that is the trivial requirement. Okay. Now we classify the PDE into three categories. So this is called 4.8. Okay. The semi-linear, PDE, okay, is said to be hyperbolic. All right, it's said to be hyperbolic, or parabolic. Okay, or elliptic. Okay, at the point, say x0, t0 in U, in the open set U, if the discriminant p, the t square, x0, t0 minus 4ac at the point x0, t0, right? If this determinant is positive, right? So if this quantity is positive, then we say that the PDE, this semi-linear PDE, is hyperbolic at the point, at this point. Or if equal to 0, right? So if this quantity is 0, then we say this semi-linear PDE is parabolic at this point. Or negative. So if it's negative, then this PDE is called elliptic. All right. So respectively. Right. So you can say talk about that this semi-linear PDE is hyperbolic or parabolic or elliptic at a certain point, according to this quantity. Okay, according to this quantity. Furthermore, the semi-linear PDE, okay, is said to be hyperbolic or parabolic or elliptic. Right? On an open subset V of U. Alright? So U is a bigger open set and V is smaller open set. If it is hyperbolic, parabolic, or elliptic at every point in V. Okay? So it is possible that this semi-linear PDE is hyperbolic or parabolic or elliptic on an open set. If it is hyperbolic or parabolic or elliptic at every point in this open set V. Alright, and so we will introduce suitable coordinate transformation, okay, to this semi-linear ODE when on some open set V, if this PDE is hyperbolic or parabolic or elliptic, because in different situations we have to make different coordinate transformation. Okay, we have to go. And so now we were dealing with coordinate transformation, right? So I have to define what is a coordinate transformation, right? Otherwise, the idea is too bad. Okay, so I have to talk about the coordinate transformation. Now, so let me write down the purpose. So in this subsection, all right, we will reduce a semi-linear PDE, all right, to a normal form. Okay, in a suitable coordinate system. According to the type of the PDE. Okay, so basically we want to extend the idea of dilemma. Okay, so the dilemma actually select a very good coordinate transformation, transform the wave equation to very simple PDE, and so that we can find a general solution immediately. But to generalize to a second order semi-linear PDE with two variables, we have to do the job according to the type of the PDE. Okay, so different type of PDE, but introduce different kind of coordinate transformation. Okay, now before discussion, okay, coordinate transformation. Okay, we need the inverse function theorem. Okay, so let me write down the theorem for you. Okay. Assume we have a vector function with n components. Okay, be a continuously differentiable mapping from an open subset U of Rn into Rn. Okay, so basically, we are talking about a mapping from a dimension, from an open subset of n-dimensional. So, for example, to okay. Okay, so just like that. So we have, for example, an n equal to 2. So you have U here, and this is an open set in the plane, and with this vector mapping. So a point here, goes to a point here. Okay, we can think about that. All right, and the V is equal to f of x1 of y, and the W equal to f2 of xy. Okay, so that is the vector mapping. And this is the situation we have. And we assume this mapping is continuously differentiable. Means what? Means that the partial derivative of f1 and f2 with respect to x, y, etc., x1, x2, etc., they are all continuous functions. Okay? They are all continuous. So this is the meaning of the continuous differentiable. So all the positive, the first order positive derivative are continuous functions. Okay, so this is the setting. If the Jacobian determinant, okay, J F A, okay, not equal to 0 for some point A in the open set U. So suppose the Jacobian determinant. Why is Jacobian determinant? It's the determinant of the Jacobian matrix. And do you remember what is a Jacobian matrix? When you were a freshman, I believe you learned multi-variable calculus, right? I believe so. Okay. But if you forgot what is Jacobian matrix, please raise your hand. Okay, good. Don't be shy, right? It's very common, right? so I will. Okay, I will write it down for you. Okay, so the Jacobian determinants. Okay, let me finish the statement first. Okay, the Jacobian is not equal to 0 for some points A in U. Okay, then then there are, alright, so now we can, there are a neighborhood, alright, the neighborhood, okay, V of A, okay, so now we have A here, this is A, right, A here, alright, and we know the Jacobian determinants, okay. It's the Jacobian determinant is not equal to 0. Then we can find a neighborhood of A. So the neighborhood of A, let me write it down. Probably here, this, okay. This is V here. We can find a neighborhood here, and of course the A map to here to a point. We call F A, right? This is the point A. So we find a neighborhood of A and a neighborhood of called W of F A. Okay, so F A. Okay, F A, and we find a neighborhood, say here, and called W. Okay, so we can find a neighborhood of A, right, called V, a neighborhood of this point F A called W, such that the vector function F, okay, is 1-to-1. Okay, on V. Okay, so it's 1-to-1 on V, and the range is equal to W. So the mapping, when we restrict the mapping to V, it becomes to 1-to-1 and onto. Okay, this is amazing because the only condition we require is that the Jacobian determinants at this point is not 0. Okay, so locally, any such a continuous differentiable mapping is 1-to-1 and onto. Right? Very nice mapping. Right, and the inverse, right? G of F. So we have inverse, right? So now we have inverse. So we have inverse here. So this is G. Okay. This is F. So now the inverse of F, of course, is defined on what? On W. Locally, right? So we define only on W here. By G of F x equal to x. Okay? For all x in V, alright, is also continuously differentiable. Okay, on W. Alright, so the inverse mapping now we are able to construct inverse because it's all 1-to-1 onto. Once we have 1-to-1 onto function, we can construct the inverse mapping locally, right? So this is local mapping, alright, just on W. And this inverse mapping is also continuously differentiable, means it is very smooth. So that is it's called the inverse function theorem. Alright, so let me address remark. The Jacobian matrix, right? The Jacobian matrix of F at a point A Okay, x defined as, so the term is here, df a, right? df a is a matrix, all right? Consists of all the partial, first order partial derivatives. So x1, a, f2, x1, a, fn, x1, a. Okay, so the first column consists of all the first order partial derivative with respect to x1, the first coordinate value x1. Okay, and we have f1, f2, and we have n components here. Oh, I'm sorry, let me say this is transpose. Because we usually describe a vector as a column vector. Okay, as a column vector mathematically usually. So this is really a transpose, the column. So I'm sorry, I have to put T here. Okay. So I have to put. Okay, and so this is the first column. The second column is the partial derivative with respect to x2. Okay. It's Fn and yeah. So I'm sorry, 1. Okay. 1 xn, and this is f2 n. Okay, so that is the matrix. So this matrix consists of first order partial derivatives. Okay, we have n squared such first order partial derivatives. Right? We have n squared, n times n. Right? And all the partial derivatives are evaluated at the point A. So this is called the Jacobian matrix of the vector mapping at the point A. The Jacobian matrix. And so the Jacobian determinant all right, at A of the vector function at the point A is the determinant of the Jacobian matrix D F A of F at A. Namely, the Jacobian determinants of F at A is equal to the determinants of D F A. Okay? So the determinants F. Okay. Any questions about the statement? So this is the inverse function theorem. So the important thing is that we can locally for any such continuous differentiable mapping. Such a differential mapping is local. If we find a point that the Jacobian determinant is not zero, then locally at this point, the mapping F is 1-to-1 and onto. Okay, it's 1-to-1 and onto. And so that we can construct an inverse mapping locally. Okay, and this immediate mapping is also continuous differential. A nice inverse mapping. This is the idea, very simple, right? This is my idea. Alright, and And the chicken criterion is just the Jacobian determinant. So even though it's, you have to evaluate determinants if n is big, right? Because this is n times n matrix. So you have to evaluate the determinants. Okay. Okay, so now a vector valued function VW. Okay, so we consider two-dimensional case. Because our case is much more simple, just to that. This is for any dimension. Okay. So let me just nail down a problem, saying that it's called. So actually, this one can be extended to n dimension, but let me just specialize to two dimensional. I think you can generalize the idea. Called coordinate transformation. Okay. Right. So on an open subset U of R2, okay, if it has the following three properties. The properties. One, okay, both Vxt and Wxt are continuous differentiable. Okay, so basically this vector mapping is continuously differentiable. Second, that V and W is 1-to-1 U. Okay, so this is 1-to-1. And third thing is that the Jacobian determinants J VW of XD. So this is the Jacobian. Okay, this Jacobian, so this determinants is okay. So the Jacobian determinants is non-zero. Alright, for every point xt in U. So this is very strong. Okay, that the mapping is differentiable, continuously differentiable. Okay, and the mapping is 1-to-1. Okay, on U, so it's 1-to-1. And the third one is that the Jacobian determinants always non-zero for all xt. From here, you can see that. Because V and U are continuously differentiable, so the Jacobian determinant actually is a continuous function. Okay, let me say that. So you can see that this is a continuous function. Okay, so it's a continuous function on U. And the continuous function never zero. So this implies that either the Jacobian are all positive for all points, or the Jacobian are all negative for all points. Okay? There is no other possibility. Because if it has value, positive value, negative value, by continuity, it must have zero value. Okay. This is called intermediate value theorem, right? For continuous function. So this is very strong. I'll just give you the consequence that so 1, 2, 3. So if we have a mapping satisfy these three, having these three properties, then we call such a vector mapping a coordinate transformation. And this one can be generated n-dimensional, right? Very easily. First of all, if we have a vector mapping, all right, and we can use F here from an open state in Rn to Rn, such that the vector mapping is continuous differential. Second, the vector mapping is one-to-one on U. The third is that the Jacobian determinants are always non-zero. Then it is the coordinate transformation. Okay? Okay. Remark. For a coordinate transformation, VW on an open subset U of the XD plane. Okay, so suppose we have a coordinate transformation. Then its range U prime VW of U. So the range of this mapping, okay, is also an open set. Okay, it's also an open set. This is a very strong property. Okay, and okay, I will give you the reference in my lecture notes. So I just tell you that if we have a coordinate transformation from an open set here to R2, then the range in R2 is also an open set. Okay, so we have open set to open set. Now, by the inverse bumping theorem, the inverse mapping okay, the inverse mapping XD, which is the inverse mapping of VW, right? The inverse mapping becomes XT. This is from U prime to U, because now U prime to U, they are 1 to 1 and arm 2. Okay? 1 to 1 and arm 2, and U prime is also open. U is open. It's also, so this inverse matrix is also continuous differentiable. Okay? But the assertion here is continuous differentiable. U prime. And the Jacobian matrix of Alright, so this is the Jacobian matrix of the inverse mapping XD at VW. Okay, right. So this is the I have to say this is the XD, the inverse mapping. Okay. So this is the Jacobian matrix times the Jacobian matrix of the mapping V and W. Okay. This Jacobian matrix. Comes to an identity by the chain rule. Okay. This is from the chain rule here. From the chain rule. If you take the differential. Okay. So by the chain rule, the Jacobian matrix of the inverse mapping, right, times the Jacobian matrix of the mapping VW, well, it becomes to identity matrix. Okay, it becomes the identity matrix here. Okay. So it's quite easy to find the Jacobian matrix of the inverse mapping, because the Jacobian matrix of the inverse is just the inverse of the Jacobian matrix of the original mapping. Okay, so that's what we have. Okay, let me take an example. Wow, it's almost going to the end of the class now. Maybe I omit example because you can see my example in the lecture notes, because wow, it's too much. Okay, because I have to get to the point. Otherwise, I will be a lot behind my schedule a lot. Okay, good. Okay, so now we go back to our semi-linear PDE. Okay, and now we will try to find suitable coordinate transformation. This is our mission. Okay, so assume. Okay, so all these are background information. Okay, about okay. I think that is necessary. Otherwise, you were not able to understand what I'm talking about in the discussion. Assume that the solution U of xd of the semi-linear PDE in 12.4.8 is twice continuously differentiable. Okay, on an open set U of the xt plane. Alright, so we assume our solution is where we have at least an open subset of the xt plane. So our goal, okay, is to find twice continuously twice continuously differentiable coordinate transformation. Because coordinate transformation is quite are continuous differentiable, just continuous differentiable. But we would like to have coordinate transformation which is twice continuous differentiable. Means that all the second order particle derivatives are all continuous. Okay, so to find twice continuously differentiable coordinate transformation. V and the W, okay, on an open subset, at least, right? Because of V of U, okay, such that the semi-linear PD, okay, in 4.8 can be reduced, okay, to a simpler form, simpler standard form. Okay, to facilitate the solution. Okay. So now, so we are going to find it, right? Find a suitable coordinate transformation which we require to be twice continuously differentiable. Okay. Now, so if such a coordinate transformation exists, okay, so if such a VW exists, okay, its inverse, right? Its inverse as which it has the inverse, right? So its inverse, we know inverse is xt, okay? It's also, okay, twice continuously differentiable coordinate transformation. Okay, the V prime is just the mapping of V through the coordinate transformation VW. Okay, and so the inverse mapping is also a coordinate transformation. Okay. So we then let U delta VW equal to U x VW y T. Okay, for all V prime. Okay, so we establish. So we have coordinate transformation between V. The V is an open set in the original xt plane, and we have V prime by the coordinate transformation to the so-called VW plane. Okay, and to another coordinate system. Right, and so we define. So we let this is the situation, and of course, which it's twice continuously differentiable. Okay. Week1. So that uxt, all right, then can be returned back to the u tilde by this information. Okay, so we have that. Okay, so the idea you can see is the same as the idea of Limburg. Okay, so we have that. All right, and so by chain rule, all right, we have a lot of data to write down. So ut as before, vt, okay, that plus u filter w and the wt. Yeah. But right now we don't have an explicit expression for the first partial derivative of v and the w. Okay, we don't have that, so we have to keep the notation here. Okay. And the ux, it's u filter v and vx plus u filter and the wx. Okay, we have that. And for utt, okay, utt is that so we have u filter vv ut plus u filter vw t vt plus u filter v, this one, and the v dt. Okay, so here, because in general this is also a function of x and t, right? So you have so these two terms. When we take the partial derivative with respect to t, we have the partial derivative with respect to this one. So we have that times this one, and also this one times the partial derivative to vt. So we have vt here. Okay. So it is a little bit complicated. So we have to be very careful. T plus u w and okay, so this is udt. Okay, and the utx is equal to vv vx plus u with vw and the wx, okay, and the vt plus v filter and the vtx plus u filter and vx plus u filter x t plus u filter w and the dx. Okay. And the last one is uxx. And this is u filter vv vx plus u filter vw x, and this is vx plus v vxx plus u filter w vx plus u filter w x and the x plus u filter w and the wxx. Okay, so you have very long by chain rule, so you have a lot of things to write down here. So now by substitution, Okay? The semi-linear PD, right, in 12.4.8, okay, on V becomes 2, well, so you will see you have A Vt squared plus B Vt Vx plus C Vx squared. Okay, so you have that, and the U Vv, this term, plus 2A Vt of T plus B Vt of X plus B Vx of T plus 2C Vx of X, and this is U filter Vw, okay, plus A of T B of T of X C of X squared U of squared. Okay, right? This is equal to F, and we have F tilde and V and W U tilde U V tilde U W tilde. Okay, this is all we prime. So the transformation. So we transform that to an equation defined on a new coordinate system. All right, and especially on this open set V prime. All right, and the F tilde actually is very complicated, so I don't write down here, but I do write down it. Okay, in my lecture notes, very long. Okay, try. Okay, so now is, and the observation here is that you can see these two have the same format, right? This one governs the V function, the coordinate, the V coordinate system, right? The V coordinate. So I think, yeah, the V coordinate. And this governs the W coordinate in the new coordinate system. That they have the same form, A and B and C here. Okay? They have the same form. And for the mixed product term here, okay? And we have that very complicated things here. Now, Lempert's idea is that, well, you try to find suitable coordinates, so we have to find such that this term and this term disappear to 0, right? Okay? When this go to 0, then we have only the mixed second order particles here only. This is the Lempert's idea. Okay? And so we will learn from him, right? To try to find a V and a W such that these two factors go to 0. This is the key idea. Okay, this is the key idea to have that. So, and okay, I think I can't finish that. Okay, so the idea. Can you 5 minutes more before we leave the classroom? A little bit. The condition. So if the semi-linear PD, okay, is hyperbolic, okay, on V. Suppose it's hyperbolic on V, means that the discriminant V squared minus 4A xd cxd x greater than 0 for all the points in V. Suppose this is true. So the semi-linear PD is hyperbolic. Okay. Then, in this case, Then the coefficient. All right. So then the coefficient of U filter VV and U filter WW can be made, right, identical when identical to 0, okay, on week 1. Namely, we can have A Vt squared plus B Vt Vx plus C Vx squared equal to 0, and A Wt squared plus B Wt Wx plus C Wx squared equal to 0. Okay, identical to 0. Okay, so we can basically go to 0 by what? By making, okay, we have Vt equals to minus B plus square root of B squared minus 4AC divided by 2A dx, and Wt equal to minus B minus square root of B squared 4AC divided by 2A. Okay. So if we relate, we are trying to find V and W, right? So we relate V and Vx, Vt, these two partial derivatives has this relationship. Okay? So we want V has first order partial derivative satisfy this identity. We want the W, right, has partial derivative satisfy this identity. If this is true, then you can check that both equations equal to 0, and then it's perfect. Okay, so this is the way, right? So now we have the clue how to find V and how to find W. Even though we at this point we only have the relationship between between the first partial derivative, the first order of V with respect to T and X here. But from that we will see next week that how to get into find the V and find the W. Okay, the coordinate system from these two equations. Okay, so we will try to find that. Alright, but at this point, you know the clue, right? We set it, and this is possible because that our semi-linear PDE is valid because the discriminant is positive. So the square root is real number. Okay, it's real number. Okay, so I have to finish at this point. I'll stop here, and I will continue to discuss the rest of the subsection. Okay, so I'll see you next.